Hi, and welcome to Agile AI Solutions. I'm Rick, founder of Agile AI Solutions. I've always been fascinated by how systems work, especially when you can break them down, understand them, and make them perform better. AI is no different. The real power isn't just in the model, it's in how you communicate with it. That's where prompt engineering comes in. This is the first course in the Prompt Engineering Primer series, designed to help you build a strong foundation in crafting powerful, precise, and effective prompts. But before we begin constructing prompts, we need context. Prompt engineering didn't appear out of nowhere. It stands on decades of progress in artificial intelligence. To truly understand how to engineer prompts effectively, we must understand the history of AI, how it evolved, what shaped it, and why it works the way it does today. That perspective will give you an advantage. So settle in, and let's begin our journey into prompt engineering. Artificial intelligence did not just appear one morning and decide to change the world. It has been evolving quietly and sometimes loudly for decades. Today, AI powers recommendation systems, helps doctors diagnose disease, translates languages instantly, and even assists in creating content like this course. But to truly understand where we are now, we need to step back and appreciate how we got here. This journey begins with curiosity, human curiosity about thinking, reasoning, and intelligence itself. In this course, we're going to explore the origins of AI, the pivotal breakthroughs, and the foundational ideas that allowed it to move from theory to research labs to everyday life. AI didn't happen overnight. It was built step by step by mathematicians, philosophers, engineers, and dreamers. And now we are part of that story. Let's get started. At its core, AI is not magic. It is built on principles from computer science, mathematics, and cognitive science, the science of how humans think. When we talk about AI, we're really talking about systems that learn from data, recognize patterns, make predictions, and optimize decisions. The major pillars of AI include machine learning, where systems learn from examples; natural language processing, where machines interpret and generate human language; computer vision, where machines interpret images and visual information; reinforcement learning, where systems learn by trial and error; and deep learning, where neural networks with many layers discover complex patterns. All of these disciplines form the backbone of AI research and development. If you understand these foundations, you understand the engine behind modern AI. The term artificial intelligence was first coined in 1955 by John McCarthy at Stanford. He defined it as the science and engineering of making intelligent machines. That definition still holds, but today it means much more. AI now includes systems that can recognize speech, translate languages, make decisions, interpret images, drive cars, generate art, and yes, even help teach you about AI. At its heart, AI is about mimicking aspects of human intelligence using machines. But here's the fascinating part: AI doesn't think like humans. It computes. And through computation, it can simulate intelligence, sometimes in ways that surpass human capability. Long before computers existed, humans were fascinated with reasoning and automation. In the 4th century BC, Aristotle developed formal logic, systems of reasoning that allowed structured thought. Euclid developed algorithmic thinking and geometry. Centuries later, inventors like Al-Jazari built programmable mechanical devices. Leonardo da Vinci sketched mechanical automata. Descartes explored the philosophy of mind. Then in the 19th century, Charles Babbage designed the analytical engine, a mechanical computer. And Ada Lovelace realized something profound. She saw that machines could manipulate symbols, not just numbers. That insight planted the seed for AI. AI began not with electricity, but with ideas. Before AI officially had a name, the foundations were already forming. In 1943, McCulloch and Pitts introduced a mathematical model of artificial neurons. This was groundbreaking. They showed that logical reasoning could be modeled with simple binary units. Then came Alan Turing. Turing introduced the concept of a universal machine, capable of computing anything computable. He also asked a famous question: can machines think? To explore this, he proposed the Turing test, a way to evaluate machine intelligence. At the same time, electronic computers like ENIAC and Colossus were being built. For the first time, machines could perform complex calculations at scale. The theoretical and the physical had finally met. AI was ready to be born. The 1950s marked the official birth of artificial intelligence as a field. Researchers began exploring machine learning, systems that could improve with experience. 3 major learning paradigms emerged: supervised learning, learning from labeled examples; unsupervised learning, finding hidden patterns without labels; reinforcement learning, learning through trial and error. Meanwhile, natural language processing began taking shape. Could machines understand speech? Could they translate languages, Search and optimization algorithms were developed to efficiently explore possible solutions instead of brute force guessing, and philosophers began asking deeper ethical questions. What does intelligence mean? Should machines reason like humans? The field was ambitious, maybe even overly optimistic, but the spark had been lit. The 1960s and 1970s were decades of expansion. AI systems began classifying text, recognizing images, planning robot paths, and even engaging in simple dialogue. Expert systems became popular. These systems encoded human knowledge using IFTN rules. For example, IF symptom A and symptom B are present, TAN diagnosis may be X. These systems were powerful but brittle. They worked well within narrow domains, but struggled outside them. At the same time, robotics advanced. Algorithms like F made efficient pathfinding possible. Computer vision improved with image segmentation and object detection. AI was learning how to see, move, and reason. But progress was slower than expected, and funding eventually declined. This period taught researchers a valuable lesson: intelligence is harder than it looks. The 1980s and 1990s brought renewed momentum. Machine learning techniques matured. Support vector machines improved classification. Language models began predicting word sequences. Ontologies formalized knowledge representation. And then something dramatic happened. In 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov. For the first time, a machine beat a human champion in a complex intellectual game. Around the same time, Google emerged, built on intelligent search algorithms. AI was no longer theoretical. It was visible. It was powerful. It was real. The 2000s changed everything. Data exploded, computing power increased, and neural networks grew deeper. Deep learning allowed systems to automatically extract features from raw data. Convolutional neural networks revolutionized computer vision. Sentiment analysis helped interpret human emotion in text. Content recommendation systems personalized media consumption. Healthcare analytics improved diagnosis and efficiency. AI was no longer rule-based. It was data-driven. The more data it saw, the better it became. Today, the foundations are firmly in place. Reinforcement learning combined with deep neural networks has achieved superhuman performance in complex tasks. Generative AI can create images, music code, and text. Explainable AI attempts to make decision processes transparent. AI integrates with the Internet of Things. Autonomous systems navigate real environments. And researchers are even exploring quantum approaches to AI. But alongside innovation, ethical questions grow louder. How should AI be governed? How do we ensure fairness? How do we build responsibly? AI is no longer just a technical field. It is societal infrastructure. And the story is still being written. We've covered a lot of ground in this course. You now understand how artificial intelligence evolved, not as magic, but as structured engineering. That perspective matters, because prompt engineering is not about guessing what works. It's about understanding the system you're working with. And now we move from historical context to applied skill. In the next courses, you'll begin developing the practical techniques that define modern prompt engineering: structure, clarity, precision, verbs, adjectives, roles, and context. These are tools. Tools that enhance collaboration, accelerate workflows, and produce targeted, reliable AI outputs. The advantage belongs to those who can communicate with AI intentionally, and that's exactly what we're building. I'll see you in the next session. And if you found this course valuable, consider liking the video and subscribing to the channel. That helps me continue building practical, structured AI education.